Beams primarily resist transverse load. For this reason, internal forces are mainly in the forms of shear force and bending moment. Functions of these forces are determined during structural analysis. In this video, we will demonstrate the method to derive these functions. To inspect the internal forces, we will cut an imaginary section through member. By doing so, we expose three forces acting on the face of section, which are axial, shear, and moment. We consider tension to be positive axial force, just like what we do for truss members. Shear force is positive if it tends to rotate the structure in clockwise direction. For bending moment, we regard sagging moment as positive and hogging as negative. We always assume there are non-internal forces acting in positive manner at the beginning and let calculation to prove otherwise. Let's look into this simply supported beam. Assuming we have determined the support reactions. Since we are determining the internal forces along the span, we will be expressing these forces as functions of location x. In some cases, there might be a point where these functions change. We need to identify those points and use them to segmentize our structure. In this example, the first point is where the load Ax, the function of shear force and bending moment, remains consistent until this point. We need to introduce the concentrated load into the functions if we go any further towards joint B. The second point is located at the starting point of load B. Beyond this point, we have to consider uniformly distributed load B. The third point is located between load B and C. The function of distributed load changes if we move any further towards support B from this point. With these 3 points, we split the beam into 4 segments. Let's check out the first segment. In this segment, we only have reaction force at support A. By using equilibrium equation, the magnitude of shear force equals to the support reaction. Bending moment equals to the product of that reaction and x. These functions are only valid for this segment. When we are dealing with concentrated loads, bending moment is a linear function of x. Shear force, on the other hand, is a constant function. This is shown for first and second segment. When uniformly distributed load comes into play, like what we see for third segment, shear force becomes a linear function of x. Bending moment, on the other hand, is a quadratic function of x. For the fourth segment, let's try to view it from another perspective. This time, our reference origin shifts from point A to B. Sometimes, this operation is necessary to avoid producing complicated functions. This time, we have varying distributed load. For this kind of loading, shear force is a quadratic function, while bending moment is a cubic function. Now, you might have noticed that we can obtain shear force function by differentiate the bending moment function with respect to x. Therefore, given a non-constant shear force function, the bending moment will be the most critical at the point where shear force is 0. These internal force functions and correlation are very useful during construction of shear force and bending moment diagrams. In next video, we will demonstrate how to develop diagrams using these functions. Thank you for watching. If you find this video helpful, please share it with your friends. We'll see you guys soon. Goodbye.